Hi folks, it's Mr. Robeson here. Today we are continuing on using integrals to find things. So we're going to go over how to find the average value of a function. We're also going to talk about the second fundamental theorem of calculus, which, I mean, you probably should have seen that coming when we called something the first fundamental theorem. It's a good idea. There's probably a second one. There's only two though. Those are the first and second. That's it. We're going to work on evaluating definite integrals using substitution, and we're going to take a look at even and odd functions and definite integrals. All right, so the average value of a function, which is related to mean value. Remember, mean and average are kind of like the same word. So the average value of a function f from a to b is the integral from a to b of f times 1 over b minus a, like divided by the length of the interval. In other words, we're finding the area under this curve, the pink part here. And then we're saying, okay, well, what's the average height? What rectangle, the height of the rectangle here, we'll say h, would be multiplied by this length, b minus a, to give us the same area. And that happens to be the average height of this function f. So if we ever want to know what the average value of a function is, we're integrating from a to b and dividing by b minus a. Right? This is very similar to the mean value theorem. Remember, the mean value theorem said f prime of c equals f of b minus f of a over b minus a. And this was just the derivative of the average derivative or average slope on the interval from a to b. All right, well, this is basically that with one higher function up. So this would be like f of b minus f of a over b minus a, and this equals to f of some height in here. All right, so it's just one function higher doing the mean value theorem. So we're doing it with integrals instead of doing it with a derivative, but it really is the same kind of thing. So really what you do want to do is just memorize this formula here, but if you know what's going on, you can derive the formula in your head pretty quickly. All right, so find the average value of this function on the interval from 1 to 4. Well, that would be 1 over, so this is a, this is b, so it'd be 4 minus 1, the integral from 1 to 4 of 3x squared minus 2x dx. So this is going to be 1/3. Now we're just going to integrate this. We get x cubed over 3. Those 3's are going to cancel out. Minus 2x squared over 2. Those 2's are going to cancel out. And this is evaluated from 1 to 4. Don't forget the 1/3 out front. So we get 1/3. We plug in 4. We get 4 to the 3rd minus 4 squared. Minus, I'm going to go ahead and throw some brackets in there because the 1/3's all the way out front. I don't want to forget about it. Plugging in 1, we get 1 cubed minus 1 squared. All right, so that's going to be 0. This is 64 minus 16, which I believe is 48. 1/3 of 48 is, I believe, 16. So that means the average value of this function between 1 and 4, the average height of this curve, this parabola, is about 16. Well, is exactly 16. I guess I shouldn't say about. It is 16. All right, now the second fundamental theorem of calculus. So it's really saying is that the derivative and the integral, they do cancel each other out and give you the function that's inside. All right, but what we need to do in order for it to get the actual function that's inside is we need to be integrating to some x. All right, so what's actually happening here is like we're getting this capital F of t evaluated from a to x. So this would be capital F of x minus capital F of a. And we want to remember here that the derivative of capital F of t is lowercase. So now if we take the derivatives, we got x instead of t. All right, so the derivative of capital F, because we're taking the derivative out in front here, derivative of capital F of x is going to be lowercase f of x. And the derivative of f of a, this is a constant. So this is just going to be our minus 0, so we don't have to put it. So as you can see, we do get the function that's inside, which is this plugged in as our new variable. All right, now most of the time, remember most of the time when we take derivatives, we're actually doing a chain rule. So most of the time it's not just going to be x up there, it's going to be some sort of other function of x, like x squared or x cubed or sine of x or something like that. So what ends up happening is, yeah, we plug that in for t, but then we have times the derivative of whatever's up there. All right, and you can derive it the same way. Like we get capital F of t when we take the integral from a to g of x, and then we plug it in. Don't forget we're taking the derivative in front of that. We get capital F of g of x minus capital F of a. If we take the derivative now, this guy is just 0. We take the derivative of capital F, we got lowercase f. With that new function inside of it, it stays the same. And then since it's a chain rule, times the derivative of the inside, and that's where this guy comes from. All right, but I usually like to remember, hey, we're just, whatever the top number, we're just plugging that in and multiplying by its, or the top function. We're plugging that into f, and we're multiplying by its derivative because it's a chain rule. If the x is on the bottom, then you got to do some, remember, integral rules. So like, remember, if you switch the bounds, equals the integral from negative the integral from b to a. All right, and some other things is this variable should always be different from this variable. So like if you're using x in here, you can use t up there. If you're using t in here, you can use x up there. All right, just they need to be different. All right, so an example, we want to take the derivative of the integral from 0 to x of the square root of t squared plus 1 dt. We could try and integrate this. It's not an easy integral to do. In fact, we have not gone over how to do this sort of integral yet. All right, but I know once I take this integral, we're going to take its derivative, and it's going to bring us right back to this function, and it's just going to plug in x right there. So we can just say that the answer to that is the square root of x squared plus 1 without any work. Done. It's too easy, right? This one here, again, we're going from a constant down here to a variable up here. We're defining this as some new function, capital F, doesn't matter. So we're going to take this and plug it in because we're trying to find the derivative of that. All right, with respect to x, because x is our variable. So if we take the derivative of this integral, we're again plugging in these x to the third. So we get cosine of x to the third times the derivative of the inside, because this function, this x to the third, has a non-trivial derivative, 3x squared, and that gives us f prime, the derivative of the original function. Now this guy was actually times 1, but we just kind of leave it off because the derivative of x is 1. All right, definite integrals with substitution. So we have two options when we're doing definite integrals with substitution. Option 1 is we do our normal substitution, and we just kind of leave off the bounds for a while. We go back to x in the end, and then we evaluate at the very end. So option 1 I'll do here. So we could cube this out, but it looks like u is going to be the inside guy, x squared plus 1. So that means du is 2x dx. I've got an x, I've got a dx, I need a 2. I've got to cancel it out, 1/2. So I'm getting 1/2 the integral of u to the third du. Now notice I have left off the bounds here, because if I put the bounds from 0 to 1, I might make a mistake. Actually, I would be making a mistake, because this now integral is in terms of u, and these 0s and 1s were x values. Like this is an x, this is an x. All right, so I don't want to put 0 and 1 here, because with u they would be different numbers. But now I'm going to integrate this, u to the fourth over 4 times the 1/2 out front. So this is going to be 1/8 u to the fourth. I know I'm leaving off my plus c, but I know I got these two to do in the end here. Now I'm going to go back to x's, 1/8 x squared plus 1 to the fourth. And now I'm going to add my bounds back in and say this is from 0 to 1. All right, because now I'm back to x's, so now I have my bounds again. All right, so this is going to be 1/8, plug in 1. So we get 1 plus 1 is 2 to the fourth, minus 1/8, plug in 0, we're getting 1 to the fourth. 2 to the fourth is 16, 1/8 of 16 is 2, minus 1/8. There we go, done. Or we can say that that is what, 15/8. 16/8 minus 1/8 is 15/8. Either one's fine. All right, now the other way we can do these is changing the bounds. All right, I usually like to do it this way. This is my preferred way to do it. But we can also change the bounds, and sometimes that's really the only way you can go about doing it. All right, so then du, so we're setting u equal to what's inside the square root here because that's a problem area. So we get 4x dx. So we've got an x, we've got a dx, we need a 4, so I'll put the 4 there with the x. We'll put a 1/4 out front to cancel it. Now remember, both of these are x's. So that means if I switch them to u's, u would be 2 times 1 squared minus 1. So this would be 2 minus 1 is 1. So if I plug in 1, I'm still getting 1. If I plug in 5, the other bound, definitely not going to get 5 anymore. 25 times 2 is 50. 50 minus 1 is 49. All right, so now we could say that this is the integral, or 1/4, the integral with the new bounds from 1 to 49. Now in terms of u, this would be 1 over the square root of u du, or 1/4 the integral from 1 to 49 of u to the negative 1/2 du. And now we can integrate that using the power rule. We'll get u to the 1/2 over 1/2, or times 2, evaluated from 1 to 49. So now I can keep these bounds here. I don't have to switch back because I've already switched to u's, so my answer and everything here is in terms of u's. So I get 2 times 1/4 is 1/2. We get the square root, u to the 1/2 is the square root. I'm just going to rewrite this actually, because that's really what this is. And now I'm going to this. So I'm skipping the steps I was doing in my head. I'm going to just write them out here. Minus 1/2 the square root of 1. So we get 49, or not 49 anymore. It's now 7, right? Square root of 49 is 7. 7/2 minus 1/2 is 6/2, or 3. So this integral is just 3. So the area under this ugly curve here from 1 to 5 is really just 3. All right, last thing here, even and odd functions. So even functions, if we're going from, so if f is an even function, which means this side here will match this side here, or this part here will match to this part here. It's reflective over the y-axis, right? Mirror image, like the parabola here would be like a mirror image, and it's not a perfect drawing. But like this area, from negative a, would be the same area as this. So we could rewrite this as twice the integral from 0 to a. So we could just double this area here. And sometimes that's easier. So for instance, if we're going from negative 2 to 2 of x squared, which is an even function, right, we can rewrite this as twice the integral from 0 to 2 of x squared dx, like that. And a lot of times it's easier to integrate with the 0 there. So we get x cubed over 3, no substitution involved, from 0 to 2. Plug in the 2. So we get 8/3. Plug in 0, we get 0. So we get 2 times 8/3, or 16/3. Probably easier than plugging in negative 2 and having to subtract and simplify. All right, now the other side of the coin here, so that was an even function, even functions. Now we're looking at odd functions. So they're reflective over the origin. So what happens with odd functions is the first quadrant matches the third quadrant. So if you notice then, it's this same area, but it's been turned negative. All right, so in other words, this negative area will cancel out this positive area, and we get that the area is 0, as long as we're going from negative a to positive a. So the same number in both directions. All right, so we end up getting 0. So now we take a look at this guy. Okay, so cosine is an even function because it matches left and right. Sine, though, is an odd function. It does not match. It matches first quadrant to third quadrant. And if we raise it to the third power, it's still an odd function. So an even times an odd is an odd. Just like with polynomials, an even and an odd together gives you an odd. X to the first and x squared gives us x to the third. Still odd. So this is all odd. All right, which tells us, since we're going from negative pi to positive pi, that our answer is just 0. I don't know what this looks like. This is a nasty graph. I don't want to integrate this. I'd have to break it up and do substitution with each one of them. Like sine would be my u, cosine would be my du, power rules, plugging in pi and negative pi. Or I can just realize that everything here is odd, And since it's going from the negative value to the positive value, it's just going to give us 0. So it's a neat trick if you notice it happening. It can save you some time on the AP. All right, so that is 5.3. So let's check out the homework. It's just doing definite integrals and the first and second fundamental theorem of calculus with a little bit of average value and some other stuff mixed in. All right, see you later.